Hello everyone. In this demo, we are going to see how ZEDEDA's edge management and orchestration platform can integrate NVIDIA's TAO Toolkit to provide an integrated workflow where the NVIDIA NGC models can be imported, retrained, and then deployed using ZEDEDA's edge orchestration tool across the fleet in a secure and scalable manner. Let's get started. So how are NVIDIA's TAO toolkit and ZEDEDA's edge management orchestration platform complement each other? If you see on the left side, you have the NVIDIA's ecosystem around the edge, where you have AI optimized edge computing platforms like the Jetson devices, which are optimized for the low resource constraints at the edge. And then NVIDIA has NGC model catalog, which has all the pre-trained edge AI models already used. It also supports edge AI runtimes like DeepStream and Triton. And they are common edge AI runtimes which can support a variety of AI models developed in a variety of AI frameworks like TensorFlow, PyTorch, and the Tensor environment, and then the it also supports the open neural network exchange format, that is ONNX. And then another important thing is that NVIDIA supports the TAO toolkit. That TAO stands for Transfer, Adapt, and Optimize. So this is a toolkit that can be used to import an already trained AI model and then retrain them using the additional data sets that are specifically created for the edge use case, let us say, right? And then you can retrain these models, optimize them, you can prune the model, you can quantize them, and then re-evaluate the model against the performance expectations. And then you can iterate till you arrive at the right set of right performance levels. And on the other side, so once you have this model, right, the other side you have the right side, ZEDEDA's edge management and orchestration platform, which is basically supports a variety of hardware architectures, as you can see, and it can be deployed in remote edge locations. And it supports on-premise private data store where you can store the models in a private data store. It's not exposed outside the network through the concept of private data stores inside the cloud. And it also supports, it has a native support for Jetson platforms. Uh, and it has a rich set of network connectivity options and then peripheral connectivity options and the Edge AI workflow orchestration through Edge AI application profiles. So you can basically combine different components that form the Edge AI solution and define an Edge AI application profile. And you can do all these things from a remote, from the centralized management platform, and you remotely manage these deployments and then monitor the performance of these deployments from a centralized location with a single pane of glass. And then now let's say we'll take one example in this demo we are going to take DetectNet V2 as the example model, and then we're going to go through this demo and then exercise different workflows with that. A little bit details on NVIDIA TAO toolkit. So on the left side, you see you can either bring the existing ONNX model, bring your own model, right? You can bring your own ONNX model, or you can bring one of the models that are already there and available in the NVIDIA MGC catalog. Once you bring that in, you basically start with the TAO toolkit where you train with additional data sets, and then you can prune the model and then you can quantize them to reduce the memory requirements and computation requirements. And then you can iterate till you arrive at the right set of parameters and the performance. And once you have a model trained for the use case, then you can package them and convert them into a format that can be run using the GPU, right, to take advantage of GPU acceleration. And you can once you convert these models into the TensorRT engines, you can deploy them at scale at the edge on top of the Triton inference server. This is where we will see how ZEDEDA is complementing the NVIDIA's framework, where you can take these models and then the Triton inference server, and then orchestrate these deployments across the fleet in the form of edge AI application profiles by simply clicking or triggering one workflow where it can get deployed on a number of devices. So with this, the DirectNet V2 as the example, right? So here you can see the model, right? It is basically it's a model trained using CNN, and then this model is going to detect objects and put bounding boxes. And it is once the model returns these bounding boxes as the inference output, you can use clustering algorithms like DV scan or non-maximum suppression or a hybrid approach to arrive at the high confidence outputs and then filter them and then show these bounding boxes. Here, two outputs are shown for demonstration purposes. One is to detect cars and it puts boxes around the objects. Another one is people. It can detect persons and the image frame and then mark them with bounding boxes. What are the learning objectives? Using this example model, we are going to see the following in this demo. We're going to take this model from the NGC catalog. We are going to train this with additional data sets that we are going to download separately. And then once we train, we're going to prune this model and then retrain the model again and evaluate the inference. Once we are done with the evaluation, we're going to export this model in the ONX format. And then this is without any acceleration so far. This is not using GPU acceleration till this point in time, right? After that, we are going to convert this model into a TensorRT engine format using ZEDEDA's AI API. And then basically, we are going to take this model and then convert that into a format which will use the GPU for accelerating inference on the Jetson devices. Once we have this model in the engine format, we are going to add it to a model repository and then package this along with other components that we are going to see, including the Triton server, in the form of Edge AI application profile. And once the application profile is built, we are going to use ZEDEDA's orchestration engine to deploy this application profile across the fleet using powerful techniques like tags or labels. And then once we deploy this solution across the fleet, we are going to switch to ZEDEDA's UI and then observe the deployment progress. And also we have built a demo web interface to see the inference status across the fleet and then other statistics as well that are coming from the deployments. So let's get started with the first step. Let's get started with the first step, which is to set some environment variables for our workplace. I'm executing this. So, yeah. And then we are going to set up the Docker mappings to map our environment with the mapping outside this notebook. We are going to install the TAO launcher toolkit, and this is going to take some time, but I have already set it up. So let's execute this. These are the environment. And this is basically these are the versions that we are recommending, right, for using the TAO toolkit. So this environment is already set up. This is for your reference. So this is the sample output, just displaying the info just to see that the TAO toolkit is set up. You can see the model hierarchy. These are the models that are already supported. We are going to use detect net v2 here, but you can the process is almost same for every other model that you see here. It's showing the version using toolkit version 550. Next thing that we are going to do is to download the additional data set that we are going to use for training this already trained model. We are going to train this with additional data. So first thing is to get this images from the data lake. So the data lake that we are going to use is from Kitty. So we are going to download this Kitty object detection dataset. This is basically from autonomous car driving dataset. So we are going to group these data into two categories. One is for training, and the other one is for testing. So training has both images and labels. So the label will basically the label will tell you what kind of object is seen in the corresponding entry in the image directory. So this is like a 12 or 14 gig worth of images. So it's already downloaded for this particular demo. So it says it's already downloaded. We are progressing to the next step, which is to verify the checksum to make sure the data set is intact. The verification of the checksum is going to take some time. Let's wait for that to be complete. Okay, now the verification is complete. We are going to the next step where we are going to unpack this to zip folders which contain the training data. The next step is to verify that the number of images and the number of labels are correct according to our expectations. Let's proceed to the next step where we take these data sets from the Kitty format and then convert that into the format that is TensorFlow records. That is what the training framework expects. So let's convert that. So this is the specification to convert it. Let's proceed to the next step. So the data set convert finished successfully. Let's go to the next step. Okay, now we're going to download the model, that is the DetectNet V2 model from the NGC catalog. We're making a directory for downloading it. This is just setting up the NGC CLI. I've already executed these are the available models from the NGC catalog, especially for this particular model. So for this model, there are many versions here. You can see metadata for each of these things. So this is trained using V100, and then the total size of the model, version ID. So there are many versions that you can see. This is the model, and this is the version we are going to download. As you can see, we have kept this model in this directory. We created a directory called local experiment directory. Under that, we have this model, and then under this, we have created another directory for this particular version, and you can see that it is downloaded. Now let's proceed with the next step to train this model. So there is a training spec. It already comes with this particular notebook. So as you can see, this contains four, 1, 2, 3, 4, 5 different classifications. Right? So this entire thing is coming with the model. So for this particular model, this is the spec to train. So the next step is to go for training the model with additional data. So this is the TAO Toolkit command to start training job. Here you can see the specification, how the model should be trained, and this is the directory where the model, after training, the trained model will be exported. We are calling this as unpruned because that is an additional step to prune this model, so we'll keep that in a different directory. So this is the unpruned first version of the model that we are going to keep here. The model training was I already triggered the training job. It was going to take some time, so I kept it going, and you can see that the training is complete. Let us check the output directory. We expect the model to be exported here. Yes, so you can see that we have the first version of our model, which is trained with additional data sets, is here. We're going to evaluate this with the TAO evaluate command. Let's wait for some time for the evaluation to be complete. It is trying to match. No, it's basically running the test data. We split the data into two. One is training, the other one is testing. So it is trying to now run through the testing data set and then compare the predictions. And then the execution is pass. Now we are going to prune this model further. And let's proceed with the next step. So the next step is to prune the trained model. Pruning is nothing but reducing some of the parameters and reducing the size of the model without compromising on the accuracy of the model. This manually, it needs some trial and error to get it right, because there's always going to be a trade-off between accuracy and model size. If you prune a little bit aggressively, then you might compromise on the accuracy. So here, they're starting with a pruning threshold of 5.2, basically this number as the starting point. This they arrived at after some trial and errors, and this is just a starting point. So the idea is to prune with a starting point and then re-evaluate the model to see how much accuracy is lost. If the accuracy is lost, then you might want to go back and then adjust this value to be a little bit less aggressive and then retrain the model again and re-evaluate. So this is an exercise that will go on to find the sweet spot. But in this particular demo, right, we are going to just show you the workflow on how you can go about pruning the model using TAO Toolkit and then retrain the pruned model and re-evaluate. So let's start with this value. And let us start the pruning step. We are going to keep the pruned version under this experiment directory pruned. So now this is complete. I'm going to see if it has kept the pruned version here. Yes. So next step is to retrain this model. The model is now pruned. Now we need to retrain this with the data set again and then re-evaluate. So we're going to do those two steps like retraining and re-evaluation. So let's do these two and then observe the accuracy. This is to show you how many steps are there in general to arrive at the right model for the use case. We took a pre-trained model and we are going through these steps to fine-tune this model according to the data set, and then this pruning and quantization are very crucial steps for the edge AI deployments, because this is how you reduce the model size without compromising too much on the accuracy. And especially since these edge devices are very low, not that powerful as data center servers, these steps become very important uh, in the AI model development for the edge environments. Let's start the retraining process. So this is the retrain spec. So this is going to take the retrained, take the pruned model. So this is a different spec that is used for retraining. We're going to retrain it, and then we're going to keep the retrained version here. So we kept the pruned version in a pruned directory, and then this is the version that is trained with the pruned model. So let us go and trigger the training job for the pruned version. This is going to take some time. Let us continue after this is complete. Okay, so now the retraining is complete. Here you can see that the job is successful, and we are just listing the new model. This is the model that is trained after pruning. We are going to evaluate the performance of this model now. We are going to trigger the evaluation. So you can see that the average position has changed a little bit. These numbers are also different this time. Now it is a judgment that we have to make according to the accuracy levels expected. So if this is the accuracy that is acceptable, then we can finalize this step. If it is not acceptable, then we might have to go back and adjust the pruning threshold and then redo the pruning and retraining. But this is just to show you the steps involved, right? So you can go through iterate these things any number of times till we converge at an acceptable accuracy levels, right? Now, assuming that this is acceptable for the deployment, right? So now, how do we proceed for the next step in the AI lifecycle, where we extract this model out in the format and then optimize it for the GPU acceleration? So in that stage, the first step is to get the model out from the TAO toolkit in the form of Onyx file. So that is called model export in TAO toolkit, which will convert this into the Onyx file. Execution status pass. So it exported the model in the Onyx file. Now the next step is to use ZEDEDA GA service to convert this. So why do we need to convert this Onyx model? We can just host it directly using the Triton Inference Server app. But the issue is this, right? It is not going to use it is not yet optimized to take advantage of the GPU. So it is going to still run using the CPU. So this is useful if to deploy on devices with just the CPU without any GPU. But if you want to use this or the edge device, which is already like running on very low powered CPUs, it is very if there's a GPU on these edge devices, definitely it is recommended to optimize this model to take advantage of the GPU. So for this demo, we are going to deploy this on the NVIDIA Jetson devices, which are having iGPUs. So we are going to convert this Onyx into a TensorRT engine. TensorRT engine is the format of the model which is uh, already programmed to run the inferences on the underlying GPU. We can do it on here itself in the in this notebook itself, which is running on a host with a Tesla GPU, NVIDIA GPU. But the exercise of converting this Onyx model into TensorRT engine needs to be done on the device where this model is going to be deployed, and because the conversion is closely tied to when the conversion or the programming happens, it is actually tied to the underlying. So that is the reason we cannot use it here. But that is where the ZEDEDA Edge toolkit comes in. So there is a toolkit that is uh, already supporting the conversion through an API. So we are going to use that to convert. We are going to pass the Onyx file to that API and get this converted into the TensorRT engine, and then we're going to get the engine file back. Let's go for that step. Now the model is getting converted to the TensorRT engine by the ZEDEDA TRT converter. It is going to take some time because it is going to reprogram the model and compile that in the engine format. and return the engine file back. So let's wait for the process to be complete. The output engine is also called uh, dot plan. So both the terms are used interchangeably. And a Triton inference server expects the models to be called dot plan. So model dot plan. And when we convert it, we actually convert that into a dot engine. So both the terms are used interchangeably. So we are going to copy the engine file that is generated by the ZEDEDA TRT converter into this name, right, model.plan, and that is what we are going to use for the next steps in the deployment. Let us continue after the conversion is complete. Okay, so output is already generated. So model is saved as model.plan. Model file is generated. So next, we can go to the next step of preparing an Edge AI profile, application profile, to take this model and then the Triton inference server and package them as an application to be deployed on the edge devices. So how do we use this this model in the edge AI deployment? So model is just one component, right? So we need four pieces to come together to realize an edge AI solution at the edge. So what are those components? So one is this Triton inference server. This is the common runtime that's supported by NVIDIA, and it can be deployed as a container, and it is and the Jetson has a support for that. And the second part is the model that we just built and packaged as the. So this has to be mounted as the OCI volume to the inference server. The third part is the Triton inference server exports metrics, inference metrics at a metrics endpoint. So we are going to use a helper container. We are going to use Grafana Alloy for that, which will pull these metrics from the Triton inference server and then send them to the Grafana cloud. And the fourth piece is the Edge AI application, which is going to be the demo application, which will demonstrate the AI business logic by simulating these inferences, right? Basically, it is going to take an already pre-populated video file and is going to extract frames from them and then from the video file and then stream them to the Triton inference server and then get the output, and it is going to show the bounding boxes that are generated by the model that was hosted by the Triton inference server. So the following picture shows what we are planning to do here in the form of Edge AI application profile. So we are going to have three devices, and all these devices are tagged with the same tag, Edge Device Group Jetsons. So we are going to create a profile which combines these four pieces together, and then we are going to roll that out to all these devices using a single command. And then we are going to observe the statistics coming from them, from each of these three to the Grafana Central Cloud, and the inference metrics from each of them. And then on each of these devices, you will have three containers running. One is the inference server. The other one is the Edge AI app, which is going to send the request for inference to the Triton server, and then the Alloy container, which is going to pull metrics from there from the inference server and then send them to the Grafana cloud. And the NGC models the model that we trained is also going to be mounted into this Triton inference server. So we're going to see how this is packaged. So the next step, we will see how this application profile is defined, how these four components are defined, and then how is a profile constructed in the ZEDEDA Edge AI framework. And then we are going to deploy them and then observe them from the ZEDEDA UI. and the metrics from Grafana cloud. Let's go to the next step of defining the profile. So we are ready to build the Edge AI profile using the model that we have trained. Before that, let's switch to the ZEDEDA portal um, and choose the devices that we will be using for this particular demo. So for those who are getting started with ZEDEDA for the first time, right? ZEDEDA, this is the ZEDEDA portal, and you can see the edge devices and then edge device clusters and app instances, and then the various application images that you can use for deploying on the edge devices from the ZEDEDA orchestrator. Here you can see edge nodes already. Well, filtering with the name 18A, we're going to use 18A devices which are based on Jetson for this demo. So we are particularly going to use these two, 18A AIE PX22 and then 18A SJC AGX for this particular demo to deploy this Edge AI profile. So how we are going to do this from the notebook is we are going to refer to these devices using this tag, Edge Device Group Jetsons. So we're going to match on all the devices which are matching this tag, Edge Device Group Jetsons, and I have configured this tag on both the nodes. You can see. So we are going to use this tag and then say, okay, deploy this profile on these devices. And that is how you can deploy this profile on a number of devices in one shot. And you can bring any number of devices. Here we have, for the demo purposes, we are going to deploy it on 2 devices. But let's say you have different groups of devices, you can always group them based on the tag and then use those tags to say that, okay, deploy this profile on these devices. To proceed with the next step in building the profile, we need the model repository to be in OCI volume. To do that, we are going to set up a Docker environment as the next step. So it's going to ask for the credentials, data enter the credentials, and then get started. Okay, we have logged into Docker. Now let us get started with the packaging the model that we have. So this is how you can put the model in this particular repository, right? In this directory structure. So Triton expects the model to be in this hierarchy. This is the top level folder where the models are stored, and it has to be the next level should have the model name and then the version. So you can have any number of versions for this model, and it will be like peoplenet/2/3, etc. Right? So that's how you stage these models, and this is the model repository according to our Triton inference server. So let's get started with packaging this as OCA volume and then push to the Docker Hub. Okay. So we have pushed this to the model repository. So for the demo purposes, I have already brought in these models and it's already there, and I've tagged it as NJC models. But the concept is same. You can even refer to this name, and then the Triton server will use that. So if you look at the profile that we are going to use here, right? So one is we are going to call this as before we begin, right? So you need to point this notebook to a particular ZEDEDA URL. So here we are going to use zcontrol alpha.zededa.net, and that is what we are referring, and we have already set it here. And you would need an API token to talk to the ZEDEDA orchestrator, and you can keep this token after you get it from the from the user's details section, you'll get the API token. Once you get the API token, you can keep it in a file, and we can actually we can read from there and set the environment variable. Basically, the idea is to set the URL and the ZEDEDA token in the environment variables here. And how does a profile look like? So the profile has a name to it, and then it has 4 components. One is the OCI, basically the Triton inference server OCI image. The second one is the model registry that we are going to use for the Triton server. And this is the Triton metrics agent that we have written for this demo. This is based on Grafana Alloy. It is going to pull the metrics from the Triton inference server and publish it to the Grafana cloud. And this is the demo app that we are going to deploy along with the server to demonstrate the inference requests that are passed to the inference server, and then the reply that we get from the inference server. This is pretty much just pointing to 4 containers here and then giving a name to it. And then we can call create profile API, which will create these profiles and then set up the images inside the portal, create the application bundles for each of these container images, and then add additional information like memory, CPU, and then stage them for deploying it on the fleet. Right? So let's get started with this and then execute this cell, which will create the profile. So you can see it is creating images. It is onboarding the container images onto the ZEDEDA platform. You can see Prometheus and the Grafana Alloy are used interchangeably. You can use Prometheus as well, but we are actually using the Alloy, which is a flavor of Prometheus agent. So here you can see the summary of the created profile. It has created 3 bundles, and it has got a name, UID from orchestrator, and then it is also using these bundles are using the 4 images that we passed. It has created the edge app images in the ZEDEDA portal. You can see that all 3 apps are showing up on the ZEDEDA portal. All right, so we have created the profile. Now let's go ahead and deploy this on the devices, and we are passing both. We are going to create a profile deployment where we pass the name of the profile that we have created here, that is Triton profile, and then we are going to pass the tag to match. So let's go ahead and trigger the deployment and see what happens. So deploying this profile, this NVIDIA Triton profile on the following devices. The 2 devices we saw, they are tagged with this name value pair. This profile deployment is basically rolling out all these 3 application instances on each of these 2 devices. So this is for the first device, and this is for the second device. For the first device, it has created 1, 2, 3 application instances, and then here for the second device, that is SJC AGX, it has created the corresponding 3 application instances. And this is for the information, and right, it has matched the devices with this tag, and they belong to this project. And it is using this profile ID and profile deployment ID. Now let's go back to ZEDEDA and then see whether these 3 app instances, 3 plus 3, we should see 6 app instances created. Yes. So we are matching on the name that contains NVIDIA Triton profile, so that we get to see only those instances. Now you can see that it has auto created 6 app instances, and it is going to take some time to load these these container images and get started. So we are going to come back after these application instances come online and continue from there. Okay, now the application instances have come up. You can see the 6 application instances, 3 for each of the devices that have come up. And you have the demo app, Prometheus agent, and then the Triton server running on each of these devices. You can see the device name against each of these application instances. Right. Now let us see how the inferences are done on the edge device. So the demo app exposes a HTTP interface, and we are going to log in through that through the browser to check how the inferences are working. So let me switch to the demo app page. Here you can see on the left side you can see the raw input, the feed. So we are basically simulating the inferences. This is PeopleNet model, which basically detects faces and people, and then draws the bounding boxes on the frame, and then gives the output frame on the right side. So we are basically sampling at the rate of one frame in every 2 seconds. Actually, the inferences are happening for every frame, but as a sample for showing it in this demo, we are basically pulling frames as the inferences are happening in a periodic interval, and then showing them here. So left side is the input frame, and then right side you can see that it is actually drawing the as people are walking on the street, you can see that the green boxes are around the person detected in the frame. For each of the person, there is a bounding box, and then there is there's a bounding another bounding box with a different color on around the face and detected each of the faces and detected on the input frame. So basically, you can use these instead of sending this to the cloud for inference. Right? So basically, what we are doing is we are doing this inference at the edge itself and on the Jetson using the GPU, and to basically reduce the latency. And you can use this to detect how many people are there in the frame, and then do other business logic around it, like counting the number of people on the frame, and then estimating the crowd projection, etc. Right? So, so that is the inference input and output on a sample device. We are taking this from the one of these devices, and that is PX22. This inference feed is this sample demo is from that as it is happening right now. Now let us. We also have this Prometheus agent. So Triton inference server exposes a metrics endpoint, and it is supporting a list of metrics that are related to the inference. Uh, this Prometheus agent, which is based on Grafana, Alloy, right? It is going to pull these metrics from the Triton server, and each of these agents are going to stream those metrics to a centralized location in the cloud, which we have orchestrated through ZEDEDA. Right. So each of these Prometheus agents, they have their source added as a label. So we have hooked this with the Grafana cloud. So let's go to the Grafana dashboard in the cloud. So this is the metrics dashboard, which aggregates all the metrics coming from different edge devices in a centralized location. So, so you can see here, this is the Triton inference server metrics. It supports an exhaustive list in different categories. For example, there is a inference request success metric, which basically counts how many number of successful inferences have happened and failures. So you can see these metrics here. So this is inference, NV inference count overall or number of inferences that have happened at the rate for every second. So basically it is doing at the rate of 6.52 at this point, and you can see the graph at different times. And then we also have NV inference request success, the number of inferences it has done so far and have been successful. And there has been no failures here so far. And the number, as we expect, the number of inferences done by the platform keeps increasing. If you want to see this on a per device basis, you can select this metric, and then you have the source label to differentiate. So now you see two graphs here. One is from the AGX device, and the other one is from the PX. So we have two devices on the in the fleet, and you have the breakup here on per source. So this is how ZEDEDA enables you to deploy these agents across your fleet, and we still be able to collect these metrics in a distributed fashion, and then all report them to a centralized location like this Grafana cloud or any metrics destination of your choice. And then it helps you to analyze these and then compare the numbers. For example, here, so you can see that the number of inferences by one particular AGX device is a little bit higher than the number of inferences done by the other device. Probably the Titan server itself started a little bit later on this box due to download latency, right? So that is how you can filter these things. And let's go back to the other set of metrics. So, this is another. So you can actually get all these metrics like inference request failure, inference request count. There is a count and execution count. So one is with it does not include the cache requests. And the other one is the number of inferences, uh, batch executions, basically number of batch executions. Here, for demo purposes, we have kept the batch count as one. So you probably will expect to see the same number on both NV inference count and the exec count. So yeah, so pretty much both are looking similar here. And again, the idea is that you can actually go into this and then see it on a per source, right? So you have two sources, right here. And then if you, and the Triton server supports model repository, it's not only for a single model. So then that Triton server automatically adds labels to the metrics to say, okay, what is the model that this particular metric corresponds to. So you can actually change. So here you can see that we have only one model running here. So everything points to one model, which is PeopleNet model. But let's say you are having 2-3 models hosted at the same time. Then if you want to see which model is, if you want to compare these metrics again across different models, then you can actually see this, and you will see more than 2-3 entries here, and then you can go to a particular, you can compare again with the different models in this graph. So here we're doing like for the PeopleNet model, we are doing like 5.86 counts per second. Of course, there's a lot of scope here for improvements, optimizations, but this is for demonstration video, this is the count that we are seeing from the current setup. And you can also see if you want to, model is just one. And then let's say for a given model, you can have 2-3 versions at the same time. So then how do you zoom into, let's say, comparison between 2-3 models, model versions? Right. So let's say for PeopleNet, you have two versions, right? So here you have only one version. Here you can see version 1 is the graph, and it's pretty much the same as the other one. But if you have two, three versions of the same model, then you will see two, three entries here. And that is how we can compare the performance or the metrics for, let's say, if you want to do A/B routing, and if you want to see what is the split looking like, right? So how many are going to the first version and how many are going to the second version, then you can compare them and then see, okay, this 50-50 or 70-30. Like if you want to make sure that the split is working as expected, then you can use these metrics. So that is just one or two examples, right? And basically pretty much whatever the Triton inference server supports, you pretty much get all the metrics here. It also supports CPU metrics and GPU metrics if you enable them. And then these are the metrics that are related to like how much time is spent in the queue, how many are pending at given time. So yeah. So and then this is just a representative thing, right? So you can actually have more sophisticated dashboards built using Grafana or any other framework. But the idea is that you get all these metrics stored in the central location. So that is pretty much what we wanted to cover. So basically, in this demo, what we have covered is that, uh, so basically, pretty much we covered how we started with a pre-trained model, PeopleNet model, and then we trained these with additional data that we collected from that Kitty data set. And then we retrained it. We ran the evaluation. And then we exported the pruned model in the Onyx format. And then we sent that Onyx model to ZEDEDA's AGI engine to convert that to TensorRT engine format. We got the optimized version that is capable of running on Jetson GPUs. And then we added that to a model repository. Once we have the model trained and loaded in the right OCI volume, we brought in the Triton inference server and then mounted the model volume there. And then we deployed this solution along with the demo app. And then it rolled out all these images automatically across the fleet. It created the application profile as a bundle, and then we matched against a set of devices using the tag. We rolled it out to the fleet. We waited for the application instance to come up, and then we could see that the inference is happening as we speak, and then it is getting metrics streamed from those Prometheus agents from the deployment. And then we can also see the status or samples of the inferences as a health check. So that pretty much completed the demo. And yeah, thanks for watching.